All right, guys, how we doing, AP Precalc? The purpose of this video is to just have me go through 1.1 to 1.6 topics from our Unit 1. Okay, so we'll see how this goes. If it's a disaster, I won't make any more videos, but hopefully they'll be somewhat useful. And yeah, I'm definitely willing to take feedback and let me know what, if anything, would help you as we get ready for mocks and then have the May exams looming ahead. So again, the goal will just be to go through 1.1 and 1.6. So 1.1 is change in tandem, just properties of functions. Here's 1.2 and 1.3. 1.4 is on polynomials. Actually, a lot of stuff about polynomials. And 1.6 is polynomial functions and end behavior. Okay, so I don't really have any example problems prepared. This is more to go over big concepts, but if something would help, give me a heads up. Okay, so let's just start with 1.1, change in tandem. Okay, and this is basically we're going to go through three things. What are functions? What are increasing and decreasing functions? And what's concavity? Okay, so this is 1.1. Let's write in black here. Okay, so 1.1, first thing is, what's a function? All right, so for a function, right, this basically means that one output, let me start again. Let's do this. Every input, right, and we usually use x as our input, sometimes t for time, has exactly one output. Okay, and that's y. So you cannot have, if we have a graph like this, that is not the graph of a function because it doesn't pass the vertical line test. Right here we have two y values that are being produced by the same x value. Okay, so that's just what a function is. Hopefully that's pretty easy, right? You can define them with formulas, with tables, but the key again for a function is every input, every x value can only produce one output. I guess the last thing I'll say, it is totally fine to have multiple x's produce the same y like we have here. That is totally okay, right? Because we know a lot of formulas that do that. But again, this is two different x's producing the same y. That is fine. What we can't have is one x producing two y's like this. Okay? So I'll put the vertical line test. Means something isn't a function, right? If you can draw a vertical line through a part of the graph and it touches more than once, it's not a function. Okay, increasing, decreasing, concave up, concave down. So this is easy, I hope. All right, and I'm not going to define in words, or at least writing, because these are supposed to be quick. Increasing, decreasing. So basically that just means, increasing means if we move to the right, the y values go up, right? So we could say as x increases, y increases. That's it, right? Decreasing function can look, like, well, that's stupid. That's not always decreasing, is it? Here's a decreasing function, right? For decreasing, as we move to the right, the y values decrease. Okay, so that's just what increasing and decreasing are. Now concavity, right? Concavity, and you guys will get to this more with calculus next year, but this measures the change, right? I'm drawing a delta there, the change in the slope. Okay, if the slope is increasing, you have positive concavity, or we call it concave up. Okay, both of these graphs that I have here, right, are concave up because as we move to the right, and for increasing, decreasing concavity, we talk about as we move to the right. As we move to the right here, the slope of this graph is actually increasing because it's getting less negative, right? I hope you guys can see that. Let me get like a different color here. Okay, so here it's negative, here it's negative, it's less negative. Now it's 0, right? So here, and if this trend continued, it would go up. Okay, and here we have a graph that's concave up also because even though the slope is always positive, it's getting more and more positive. Okay? Concave down, well, let's do it this way. Here's that right there that I just drew, this graph. This is increasing but concave down, because as we go left to right, the slope is getting less positive. Hopefully you can see that. So here it's, I don't know, but it's flattening out. And if we want decreasing and concave down, right, looks like that. So 0, more negative slope. Okay, so I'm going to say concave up, or positive concavity. This means the slope is increasing. Okay, and if we have negative concavity, or we have concave down, right, that means the slope is decreasing. Okay? Yeah, so that's it for 1-1. Rates of change linear and quadratic. Okay, so rate of change, right? This is our fancy word for slope, right? And it's basically the change in y over the change in x. Or sometimes if we have time as our independent variable, it's the change in y over the change in time. But that's all rate of change is, right? How is the y variable changing compared to the x? Okay? For an average rate of change, right? Let me go over here. For an average rate of change, right? An average rate of change. So for the average rate of change, we just take the value at the end. So let's say this is, I don't know, if this is 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is about 9.5. And then this is 1, 2, 3, 4, about 5, right? Okay, so the average rate of change in this graph, right, from this point to this point is 5. Right here, A rock is 5 over 9.5. Okay? Because that's the change in the y values, 5 minus 0, over the change in the x values. Okay? And that's what we've been doing before. And what you guys will do in calculus is you'll find the rate of change at a single point. Okay? How do we approximate the rate of change at a point? Well, it's simple. We try and get a point that's really close to it. So if I wanted to approximate the rate of change right here, right, what would be really nice is if I could have function values, or I could have point values very close to it, right? So if I blow this graph up and I compute the rate of change between these two, it's going to be very, very, very close to the exact rate of change at that point, right? Same thing here. You know, sometimes we can take the right point minus the left point and compute those differences, okay? But that's, for now, that's how we can estimate the rate of change at a single point, is we pick points that are really close to it and compute the average rate of change. Talked about this. Finite differences. Okay, so finite differences, that's basically just measuring how is the rate of change changing, right? So if the rate of change is constant and positive, you would have an increasing graph. If the rate of change was constant and negative, you'd have a decreasing graph. And then for concavity, we would measure the rate of change and see if it was changing or not. Okay, so for finite differences, you know, we'd have to have a table of values. So I don't even know if this is a good idea, but if we just pick a couple values, or if I just create something, this is probably a disaster idea. 0, 1, 2, 3, 4, and then I have 2, 5, 11, 23, 45, right? Well, the change in y, right? The change in y differs, and so here we have x is always increasing by 1, 0 to 1, 1 to 2. Okay, but look what happens to the changes in y. We have 3, then we have 6, then we have 12, then we have 22. Okay, so this is not linear, right? Because the change in y, when x is just changing by 1, is not constant, right? And in fact, because these changes in y are increasing, this is going to be a concave up graph. Okay, because basically what's going to happen, you know, if you start at 0, 2, and you go to 1, 5, and you go like, since the distance, since the y value distance is increasing, right, basically your graph is just going to jump farther and farther up. Okay, so it's going to be concave up. But that's, you know, what we want to think about with this finite differences, right? Can we take a table of values, keep one of them the same? We usually keep the change in x the same, and then we can explore what's happening with the change in y and get an idea of what the function's doing. Okay, so that was 1, 2, and 1, 3, really quick. Let me check that off. 1, 4, polynomials and rates of change. Okay, so with polynomials, let's define that, right? So basically, I need to add another page here, guys. Geez, can I remember how to do this? Yeah, I think I do the current template. All right, so for polynomials, right? Favorite, you guys love this very formal notation for a polynomial. Shoot, sorry. I'll just go one more, n minus 2x to the n minus 2 plus dot, 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 dot. And then I'll have a a to the 0, a to the 0. Okay? So basically, right, you have a bunch of terms. You have a coefficient. The coefficient has to be a has to be a real number. And you have an x component and you have a exponent on that x. This number has to be an integer, positive integer, right? Sorry, non-negative integer. It could be 0. So for example, technically, f of x equals 3 is a polynomial because 3 is the constant term. F of x equals 7x minus 5. That's a polynomial because we have a constant term and we have a linear term, okay? But yeah, f of x equals 3x to the 1001 minus x to the pi. That's not a polynomial now because of this x to the pi. Okay, so that's the definition of a polynomial. Now, with polynomials, right, because they can turn a bunch of times in theory, or depending, we have maxes and mins, which we call extrema, but we have global and local ones. Okay, so remember, extrema just means maxes or mins, global or absolute, local relative means where they are. So hopefully I can just draw a graph and explain it all. So let's draw a polynomial that does something like this. Okay, so from the end behavior, hopefully remember this thing has the same end behavior. It's going to negative infinity to the left. It's going to negative infinity from the right. So it's an even degree, but the leading coefficient is negative because that's the only way that we could have a graph going to negative infinity on both sides. So I'm going to say the leading coefficient, the leading coefficient is negative, and this is even degree. And I guess one other thing, right? If we look at how many times it turns, so it turns one time here. Let me mark these. So here's a turn, 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 here's a turn. So at a minimum, this thing turns 1, 2, 3, 4, 5, 6, 7 times. It has to be at least 8. So the degree has to be greater than or equal to 8. Okay? So you take the number of turns, 1, 2, 3, 4, 5, 6, 7. You add 1 to that, you get the minimum degree. So absolute means the highest on, or absolute max is the highest point on the whole graph. Right here, this is the absolute max. And remember, if they just ask for the max, that's a y value. Okay? So the word absolute, right, this means on the whole graph. On the entire graph. Okay? This thing doesn't have an absolute min. Why? Because it keeps going down that way, so there is no absolute minimum. Okay? Local max and local mins. Let me get red. So here's a local max right there, right there, right there. And what we say for a local max, right? This is on part of the graph. So it's a max on part of the graph, or you could think of it as a turning point. Turning point. Okay, so in this case, if the graph goes from increasing to decreasing and it's continuous, it has a local max. Right here, this is local min because the graph goes from decreasing to increasing. Okay, same thing here, decreasing to increasing. So let's get another point, another color. So right there's a local min, local min, local min. Okay? So this thing has to be at least degree 8. 8 minus 1 is 7. 1, 2, 3, 4, 5, 6. We have 7 local maxes, local extrema, right? Maxes and mins combined. And this local max is also the absolute max. Okay? Points of inflection. And then I'm going to stop because I feel like I've been talking too long and I'll make a second video. So let me check this now. Points of inflection. So points of inflection, these are places where the concavity of the graph changes. Okay? And you'll be able to find them next year when you take calculus. For now, we're just going to try and guesstimate them. Okay? So if I got a graph like that, and again, if I think about, like basically I have 4 shapes that a graph can be. Okay? So it looks like somewhere right in here, this graph goes from concave up, right? Water's getting held, to concave down, water spilling off. Right about here, it switches again. The water's spilling off, but now it's accumulating, okay? So these points here, right? They're points of inflection, okay? They will occur between local maxes and mins. All right. So this part of the graph here, this is concave up. Right about there, it switches, goes concave down. The slope starts decreasing. Right. At this point is another point of inflection. The slope goes from decreasing to increasing. Okay. And let's see. You would have. So I think. Yeah. Let me write this for a polynomial, right? The degree minus 2 is equal to the number, I'm not even going to say always, right? Because you guys know if possible. POS. Okay? So, I'll stop this video right now and I'll come back and do, just talk about division, the different types, and finish through 1/6. Okay? See you guys soon.